So that this is the end of the topic for clutches and disc brakes. Our next topic is drum brakes. So drum brake, or again the same theory also applies for clutches. So drum brakes are also a type of friction brake. So they also work on the principle of friction. However, the difference here is that instead of a flat plate surface, in case of the disc brake, in this case we have a cylindrical surface. So the friction material is applied to the circumference of a cylinder. So to the circumference of a cylinder, and it can be applied externally or internally to the circumference. So externally or internally, both types of variations exist. Now this type of brakes, this type of principle, it is more often used in brakes than in clutches. So more often used as brakes than clutches, right? And in the drum brakes we have two types, we can say. One is called short shoe brake, and the other is called long shoe brake. So in brakes, as I previously explained, we have a shoe, right, which comes in contact with the surface in order to apply the braking force, and you have seen it in the bicycles. So the shoe can be short or the shoe can be long, hence the name short shoe brake or long shoe brake. Now where is the line between short and long? So in case of short shoe brake, since this is a cylindrical surface and it is a circumference, we measure the angle subtended by the shoe at the center of the wheel. So if the angle subtended is less than 45 degrees, then it is called a short shoe brake. And if the angle subtended is obviously greater than 45, then it will be a long shoe brake. In order to understand this, you should go to figure 17-9 of the book, right? So let me zoom in there. So here, as you can see, we have a wheel, right? And here in gray color, you see a shoe. So this shoe has the shape of an arc here, which comes in contact with the wheel. So this is the drum and this is the shoe, and the angle subtended by this shoe at the center of the drum is represented by angle theta. If this figure is not very clear, you should go to the book, the PDF of the book, and you will have this figure 17-9. So this angle theta is what I am talking about here, which should be less than 45 degrees for this to be called a short shoe. If this shoe is longer, if this shoe is bigger, the angle subtended, this angle theta will be greater than 45, and in that case it will be called a long shoe break. So this is the only difference, otherwise the working principle is the same. So coming back, we are going to start from an analytical expression for a short shoe break, and then we will move on to the to some of the problems, and then to long shoe break. So let me start here. So the name of the topic is analytical expression for a short shoe and external drum brake. External drum brake. So we are going to call it external because the shoe comes in contact with the drum externally, to the external surface of the drum, as you will see here. So if I can draw a drum here, so the drum is a circle, right? And then we have this shoe which comes in contact with this drum, and this shoe is attached to a kind of a lever. So let me just make it better here, like this, and it is pivoted to some point here. So it will come just like this. So this is the pivot point O, right? The force is applied on one end of this lever. So this force is Fa, again actuation force, so Fa. This is our drum, while this little thing here is the shoe. So when the drum is rotating in a specific direction and it is about its center with an angular velocity of omega, and the radius of the drum, we can call it R, right? And the angle subtended by this shoe at the center of the drum is called theta, which in this case is going to be less than 45 degrees because it is a short shoe drum brake assembly. Now, in order to solve for the analytical expression of this kind of brake, we have to draw the free body diagram of this assembly, which will show us the forces that are acting at different parts of this assembly. So for the free body diagram, let's draw this lever as it is, right? And here we have a shoe attached to this lever, and it has a circular arc here, just like this. So we already know that on one end we are going to apply a force, which is the actuation force. Now when the drum rotates in the direction shown, we also have a frictional force acting at this surface. So this frictional force I'm going to show like this, and this will be F and small f. Small f is for friction, and at the same point we will also have a normal force. So friction force has two components, one this tangential component Ff and one is the normal component Fn. Now remember that in rotational friction, when we have this kind of contact, rotational contact, the direction of the frictional force is the same as the direction of rotation. It is not opposite, right? So since this is moving in this direction, the drum is rotating in this direction, the frictional force is also in the same direction because this is the case of rotation. And then we might have some reaction forces at the pivot point because this is the point where this lever is fixed. So we have two components here, Ry and Rx. This is our point. So our free body diagram is almost complete, except that we should define the distances of certain forces from the pivot point. So this distance, this first distance is called A. So this is perpendicular distance. Then we have the another perpendicular distance here, right, which is B. And the third perpendicular distance is between this force and the pivot point, which we are going to call as C, right? So this is remember, this is the same figure as 17-9 in the book. So you can see it from there. I just developed it step by step so that you would understand. So in this free body diagram, now what we have to do is we have to find out the relationship between all these forces. And one thing that we can do is we can take moment about this point O. So and sum of moments to be precise. So the sum of moment about this point O will be taken as 0. So let's take the sum of moments about point O is equal to 0, and we are going to take the counterclockwise moment as positive. Now this force A is going to make a rotational effect about this point O, and it will be counterclockwise. So we will write A times Fa. So A is the perpendicular distance, Fa is the force. Then we have this normal force Fn, and it is creating a clockwise effect about this point O. So this is B times Fn. And finally we have this point, force, frictional force Ff, which is again creating a counterclockwise effect. So Tc times Ff, and all of this is equal to 0. And from here we can actually find out a nice expression for the actuation force Fa, which is equal to Fn into B minus mu times C over A, right? Now from where did this mu come from? That is because this Ff actually, it can be replaced by this relationship mu Fn. So frictional force is equal to mu times the normal force. So when we replace this by mu Fn and put in here, we get this expression, right? And additionally, we also have the expression for the torque, right? And the torque is actually the frictional force divided by the radius r here. So this is the radius r. Let me change it to r like this, right? And again this ff is equal to mu fn, so this will be mu fn into r. So this is our relationship for torque, and here we have the relationship for the actuation force. And if you recall, in case of disc brakes, we also had two expressions, one for the actuating force and the other for the transmitted torque. So we have found out kind of equivalent relationships in this case as well. Now, using these expressions, we have to study two phenomena which are related to the short shoe external drum brake, and these phenomena are called self-energizing condition, and the other one is called self-de-energizing condition, which we will study shortly. So what is self-energizing? Self-energizing condition is what we just studied. In this case, if you concentrate, you will see that we have the applied force here, your applied torque here, A times FA, and we have the frictional force or frictional torque here, which is C times FF. And this frictional force is actually being added into the applied force because we have a plus sign here. So when such is the condition where the frictional torque is acting to increase the applying torque, this condition is known as the self-energizing condition, right? So the frictional torque is actually helping the applied torque because it is being added here. And this condition is achieved because we had the direction of rotation of omega as counterclockwise here, and here we had the drum, the shoe, and we had this kind of frictional force condition FF, right? So as you can see, I have reproduced the same here. So this is the self-energizing condition, or in other words, this is the self-energizing direction of rotation, because if I reverse the direction of rotation, so let's do it, self-de-energizing, which is the opposite of what we just seen. So in case of self-de-energizing condition, what we can show is that the direction of rotation of the drum now is clockwise, and so this frictional force direction will also be reversed, right? So this here is your shoe. So this frictional force direction is the same as the direction of rotation of the drum. Now if we try to write the same condition using the free body diagram, what we will get is, we will get the exact opposite. So we will get AFA minus BFN and minus CFF is equal to 0. So now if you note that here we have minus instead of a plus. So in this case, or in this direction of rotation, the brake is not self-energizing, instead it is self-de-energizing. So in one direction of rotation, a brake, a short shoe external drum brake, in one direction of rotation it is self-energizing. In the other direction of rotation, it is self-de-energizing. And this actually is true for the automobile braking systems where we have drum braking. So automobile braking system is self-energizing in the forward motion, right? And while they are made self-de-energizing in the backward condition. Thank you.